Yeah, I guess it's just like age. We just talked about like getting outside of cold, and he's like, I don't want to do that. It's so weird.
That made me now. I just don't know.
Because last year the bad thing, I think it would have been fine, but it's like,
Oh.
All right.
well, I think do I hang out?
Every single word.
But, yeah, like, I would-
Hey, man. No.
All right. So Laplace transforms. We now know how to compute Laplace transforms. It's really this integral that you have to compute. And we only did it by hand, this integral. We only did it by hand for this one. And you have to worry about like, depending on your S, your Laplace transform may not be defined because some of these integrals will diverge. So, there's a domain of convergence that's tied to what S has to be. So this is like 1 over S is the Laplace transform 1, with S being greater than 0. Otherwise, it's diverges, so it doesn't equal anything. It's just infinity. This one is the Laplace transform of T. And then those are the only ones we actually did by hand. The rest of them, like for instance, this one, we just reused. We saw that e raised to negative st dt was 1 over s with s greater than 0. So when you see the Laplace transform e to the at, you just notice that would have been the same thing as 1 over s, but with the s being replaced by s minus a. And then this one we also did by hand, but this was a piecewise one. And then we just kind of now started using the table instead. And the table actually tells you somebody did the hard work of computing the Laplace transforms already, and you're just going to use this. We did the first two by hand, or definitely the first two as well as the last one for t equals for n equals 1. So we've done some of these. I did talk about cosine of bt down here in class, and then I just posted the one for sine. So these are all confirming those Laplace transforms on the table. And so that's what you're going to use. There are other Laplace transforms that you now can do using this theorem right here. So there is this theorem called the shifting theorem. And suppose you wanted to take the Laplace transform. So let's say suppose you want to take the Laplace transform of this instead of, so the Laplace transform of f of t is this. This is like the definition that we have. But let's say, suppose I want to compute the Laplace transform e to the ct times f of t. Okay, so I'm just using blue to signify this new function. And so using the definition of the Laplace transform, it's just going to be just using this thing in the green box here. It's just going to be 0 to infinity of e to the negative st times the function. And for us, the function is this now. Okay, so I'm just saying compute the Laplace transform of this. This is our function. We're just going to say that is going to be our f of t. Like this is now like our f of t. And it just appears here. And then, but there's always the e to the negative st that gets multiplied, right? When you take the Laplace transform. And then when you look at this actually using using what you know about exponentials is the same as e to the negative s minus c t. I'm just combining these two exponentials into one exponential and writing it in this very particular way because it's actually going to be really nice to see what it is at this point. Okay, so now we have this. Now on the side here, I'm going to say, well, if we know that this is the Laplace transform, so capital F of S, you see this is the Laplace transform. Okay, so you see capital F of S is the Laplace transform. Why don't I just say, what is the Laplace transform of, if capital F of S is this, I could change the S to S minus C. This is like taking my Laplace transform function, and it's like doing a horizontal shift. You know how when you did function transformations, you might shift your Laplace transform or your function. This is like doing a shift. This is like a horizontal shift of, I guess, to the right by c. But if you are making this s be s minus c, then that means, of course, this is the same as 0 to infinity of e, where this s right here has been replaced by s minus c. So it's going to be negative s minus c t f of t dt. And then I'm going to make an observation that you see this right here and this right here. What do you notice about them? They're the same. So this right here is just the Laplace transform shifted by c. So that's the shifting theorem. It's saying that this right here, the Laplace transform of e raised to ct of your function, which is this right here, the same, is precisely the Laplace transform of my original function f of t, but shifted by c. So this capital F of s minus c is like taking my Laplace transform of this f of t, doing a horizontal shift on it. That's actually the same as if you took the Laplace transform of e to the ct times f of t. This is called the shifting theorem, and it's going to be possible to compute some other Laplace transforms, basically any kind of Laplace transform. If you know the Laplace transform of f of t, now with this theorem, you can easily compute the Laplace transform of e to the ct times f of t. So for example, if you do, if you're interested in computing the Laplace transform e to the minus t, so this is me copying the shifting theorem. The shifting theorem just says Laplace transform e to ct f of t is equal to capital F s minus c, where the capital F, I write down here, capital F is the Laplace transform of the original function f of t. So this one, you're going to think of this, see this f of t right here is really this guy right here. So we're going to say this is our f of t. And the nice thing about the shifting theorem is just compute the Laplace transform of this f of t. So we're going to say my capital F, the convention is that if you take a Laplace transform, it becomes capital F, and the function, the transform variable is s, you're just going to take the Laplace transform of cosine of 3t, which we already did. It's like going back and looking at the table. It's like this entry right here, but b will equal 3. So ss squared, b squared. Okay, so we'll just go down. And so, of course, here, b is equal to 3. So the Laplace transform of this is going to be s over s squared plus 3 squared. I'll just write it like this, b squared. That's the Laplace transform, but of course, for our problem, it's going to be s squared plus 3 squared, which is 9. So we'll just leave it as 9. And then I'll just do 3 squared. Okay, so that's clear, right? That's the Laplace transform of the f cosine of 3t. And then what do we do to it? What's the c? Yes, c is equal to -1. So all we're doing is just writing, we're just going to write this. So the Laplace transform of what we actually want, which is the e to the -t cosine of 3t, is going to be exactly this Laplace transform that we just computed for just the cosine of 3t, with the c being -1, which means that, well, I'll just write it f minus c, but we also know that c is equal to -1, so it's going to be minus of a -1, which is just f of s plus 1, which is equal to all the s's, right? So this s becomes s plus 1 up here. This s down here becomes s plus 1 squared, and I'll just go ahead and do 3 squared as well. So that's the Laplace transform of e to the -t cosine of 3t, just using the shift. So it's like just compute the Laplace transform of cosine 3t and then just apply the shift, knowing that, just observing what the c must have been. Let's do it for this one. This one, which was the f of t function, t squared or the e to the 2t? Going to be the t squared is the f of t. And then it's clear from here that our c is going to be 2. So you're going to apply a shift of 2 onto the Laplace transform of t squared. So you're going to compute the Laplace transform of t squared, which I'll just write as capital F of s. That's the Laplace transform of t squared. This one we saw earlier, it's going to be from this table, t to the n, n factorial s, n to the minus. We did the case with n equals to 1, n equals to 2. This is just like doing integration by parts multiple times. It's going to pop out successively lower power. Each of these exponents come down. That's why you got factorial. And the book does a few cases and then notices that there's a pattern, and this is the pattern. But the t squared case is n is equal to 2 on this. It's 2 over s cubed. So this is going to be 2 over s cubed. And using the shifting theorem, our Laplace transform of the t squared e to the 2t will just be applying a shift onto this by 2, which is just going to be 2 over, anytime you see s, they just became s minus 2. So that's the Laplace transform. Okay. You could go more, right? I got to do this quickly. So of course, this right here, this is your f of t function. You have all this exponential being multiplied to this guy. So you'll have to take the Laplace transform of this, but you know from linearity that you just have to take the Laplace transforms each entry. And so this is like saying take the Laplace transform of t cubed plus t minus 2, but that's the same as if you took the Laplace transform of t cubed plus the Laplace transform of t. I'm going to write it this way. The Laplace transform is going to be minus 2 times the Laplace transform of 1. These Laplace's transforms are all integrals, so they, you can pull the constants out. So Laplace transform of 2 is the same as 2 times the Laplace transform of 1. Just keep that in mind. Because the Laplace transform of 1, we know those. So you apply, from the table, the t cubed case is right here. T cubed is 3 factorial s, so it's going to be 6 over s to the 4th. So we have that. It's going to be 6 times 6 over s to the 4th. Laplace transform of t is just 1 over s squared. We did that one by hand. And then, of course, the Laplace transform of 1 is 1 over s, but we have a 2, so minus 2, so it's going to be 2 over s. That's the Laplace transform of this. But then you're going to use the shifting theorem, so you're basically going to say the Laplace transform of the thing we want, which is this giant thing, is exactly the Laplace transform we just computed, shifted by how much? So it's going to be s plus or minus what here? I want to make sure about the sign. What is c? So then it's going to be minus of a negative 2. So this should be a plus 2. So it's going to be 6 over s plus 2 to the 4th plus 1 over s plus 2 to the 2nd minus 2 over s plus 2. It's the Laplace transform of this. It's really not even taking integrals anymore, right? So maybe it's easier than the first couple of sections, parts where we actually had to compute an improper integral. We're just using our table where somebody did all the work. We did some of these by hand already, so we're just reusing our work for computing the Laplace transform of 1 and t cubed. But I'm making this observation that it's actually, if you had e to the ct multiplied by a function, the Laplace transform is just the Laplace transform, the original function shifted. And so that's that theorem. We're going to look at this other theorem. So the derivative theorem, let's suppose I want to compute the derivative of a Laplace transform. So of course, capital F of s is your Laplace transform. Let's say I want to take the derivative of it. Now, your Laplace transform is a function of s. So this is like taking the derivative with respect to s. When I write capital F prime of s, this is like taking the derivative with respect to s. I'll just make that very clear because our Laplace transform is a function of s. But what is the Laplace transform? So it's like taking the derivative with respect to s of going from 0 to infinity of e to the negative st f of t dt. This is just the definition of a Laplace transform. And there are theorems that show that you're allowed to, you can pull this derivative inside the integral. So I'll just say it's going to now be inside instead of outside. When I do that, I'm going to make it like, because it's a little confusing because this is like DDS, and you have S and T show up in both, there are two variables that show up in this expression in the integral. So technically, I think the right way to write this is that you're looking at the partial derivative, which I know some of you guys might have not taken Calc 3, but I'll just explain what that means in a second. This just means that I'm only going to take the derivative with respect to S. T is going to act like a constant. Okay, so we're going to pretend that T is like a constant. We're only taking the derivative with respect to S. So if we're going to take the derivative of this expression here, assuming anything that has T is a constant, what would be the derivative? So let's look at this e to the negative st. What's the derivative of that with respect to S? You're going to pretend like T is some constant. So you have to do the chain rule. What's the derivative of negative st if T is a constant and S is the variable? It's going to be negative T e to the negative st. And the f of t is a constant as well from the perspective of S being the variable. So you have this. Okay. Yeah, I mean, that's what I'll do then is you have basically, this is saying that, I'll just underline it, say this thing is equal to this. So I'll just write that down. So in the end, we have this conclusion. We could pull the minus out. So I'll just say minus integral from 0 to infinity of t e to the negative st f of t dt. This is the conclusion that we have. And why don't I just multiply both sides by negative? So it'd be negative f prime, negative of f prime of s is equal to the integral from 0 to infinity of t e to the negative. Well, I'll write it like this. I'm going to write it like, you can write this in any order. So I'm writing a negative e to the st first. Then I'm going to write t f of t dt. If you look at this integral right here, right, this integral right here, this is actually the Laplace transform of what? This is the Laplace transform of, what should I write in here? Do you remember from the definition of the Laplace transform? So the definition of the Laplace transform is 0 to infinity. It's TFT. Yeah, it's the Laplace transform of TF of t. So the Laplace transform is saying you just have e to the negative st times f of t dt. That's, let's write the integral. The Laplace transform of f of t is this. So all you're doing is you're just making an observation that this right here is this right here. So this integral is the same as the Laplace transform of t f of t. And so basically we have the conclusion that this thing is equal to this thing. I'll just do it this way. So this thing is equal to this thing. And that's the theorem here. So I guess it's right here. And so the claim here being made is that if I want to take the Laplace transform of t times some function, well, I can just take the Laplace transform of my f of t, take the derivative of it and put a negative in front. And so this capital F is just like we had with the shifting theorem. It's the Laplace transform of my original function f of t. But if I want to compute the Laplace transform of t f of t, all I do is compute the Laplace transform of my original function f of t, take the derivative of it and put a minus. It's a little worse than the shifting theorem because the shifting one, you're computing Laplace transform of the original function, and you're just replacing your s with s minus c. This one, you have to take the derivative of it and put a minus, and taking the derivative part's what a little bit of a mess. So let's do that. If we look at, every time you see a derivative of Laplace transform of t times f of t, you can just compute, like this is my f of t. I can just compute the Laplace transform of cosine of t, which I'll just say is like my f of s is equal to the Laplace transform of cosine of t, which we know it's like s over s squared plus b squared. Yeah, that you know how from the table, it's just gonna be s squared plus 1 because b is equal to 1 here. That's your Laplace transform of my f of t. Well, if I want to compute the Laplace transform as tf of t, I have to take the derivative of it and then put a minus in the front. So I'll say now I got to do f prime of s. This is taking the derivative with respect to s. There's s's on both the top and the bottom, so you have to do the quotient rule. So b low, d high. Derivative of the top is just 1, so I don't have to write that. Minus high, d low, the derivative of the bottom is 2s, over the bottom squared. Which simplifies to, there's a 2s squared, so it's going to be y minus s squared over s plus 1 squared. So from the derivative theorem, the identity says that we have the Laplace transform of t cosine of t is going to be just the negative of this. So we just compute f prime of s. I just took the negative of it. Well, I'm just going to flip the 1 minus s squared to s squared minus 1 to apply the negative. That's it. So, you know, we're able to compute a lot of these Laplace transforms. Anytime you have a multiplication by e to the ct, and anytime you have a multiplication by t of something you already know the Laplace transform of, you can do it now because you have these two theorems. All right, let's keep going. Let's do this one. This one, this is my f of t, right? So this is my f of t. And we're multiplying by t squared. So the derivative theorem, there's a general form of the derivative theorem. It's like this right here. Where does it come from? So if you're interested in computing, let's say you were to take this capital F double prime. That means you're taking the second derivative of e to the negative st. That means you're taking a derivative once, which is going to pop out a negative st, but then you're taking another derivative, which pop out another negative st. You'll have two negatives that cancel. So that's why there's a negative 1 raised to the n here. And then there's a t to the raised to the n here because instead of just one t, you would have two t's. And then you may successively, if you were to take capital F triple prime or quadruple prime, the chain rule would have required you to pop out successive terms of negative t multiple times, which is going to cause there to be t raised to n here. And then there's going to be each time a negative that pops up. And so that's why there's a negative 1 raised to the n. You can check this on your own, but in general, that is going to be what happens if you were to successively take the derivative of your Laplace transform with respect to s multiple times. We're interested in looking at this general form instead of just t because we have t squared here. And so it's like you're looking at the case where n is equal to 2. Okay, but before we even apply this derivative theorem, we know we're going to have to take the Laplace transform of e to the 2t. So capital F of s is like taking the Laplace transform of e to the 2t. So we'll just say Laplace transform of e to the 2t. This one's super easy because this is just, remember from before that it was like s minus a. And then this case, a is equal to 2. It would be 1 over s minus 2. Okay, so then let's look at the n equals 2 case. N equals 2, if we just wrote this out, it would have been a Laplace transform of t squared, which is great because that's what we're interested in, of your function f of t, is equal to negative 1 squared times the second derivative of your Laplace transform, which is like the negative 1 squared is just 1. This is like just f double prime of your Laplace transform. So the Laplace transform of what we want, which is t squared e to the 2t, is just capital F double prime. That means I just have to take the second derivative of this. So I'm just going to take the derivative, which you can just think of it as s minus, this is like s minus 2 raised to -1. So I'll just say this is the same as negative. This raised to -2, which means I can just put it on the bottom. And then derivative of s is just 1, so that's that. And then you're going to take another derivative of it, which is like, I'm going to take the derivative of, this is going to be s minus 2 raised to -2. Pull the -2 down, multiplies with the negative, so you just have +2. And then it's going to be s to the -2 raised to -3, but I'm going to put it in the bottom. And then times derivative of s is just 1. So that's it. Therefore, the Laplace transform of t squared e to the 2t is equal to, like we just said, using this derivative theorem, with n equals to 2 is just the same as capital F double prime of s, which means that we just computed it that way. It's just this. So that's the Laplace transform of t squared. Yes.
So at one point, like with the right Laplace transformation, we don't even have to calculate the Laplace transformation. So from one, and we just
Yeah. So that integral that we had to do really early on using the definition, like the actual definition was an improper integral. You don't do that anymore after knowing what the the Laplace transform of these basic pieces are. And we know now Laplace transform of 1, we know Laplace transform of t, we know Laplace transform of t squared and p cubed, and cosine of something t, cosine of b, sine of that. All of those did require using those integrals, but we're just reusing them. Coupled with these couple theorems now give us access to computing the Laplace transform of things that are multiplied by e to the ct or multiplied by t to some power. This t squared times e to the 2t, was there another way we could have done it? We didn't have to use the derivative theorem, right? We could have done the shifting theorem, because the shifting theorem would have used c is equal to 2. And actually we did do it. It's right here. So Laplacian t squared e to the 2t was one of the examples I did using the shifting theorem. We got 2 over s minus 2 cubed. Using the derivative theorem we just did right now, we also got 2 over s minus 2 cubed. I think either would have been fine for doing this one, but the shifting theorem is probably easier, because you're just taking the Laplace transform of t squared, which is just reading from the table, and then just replacing your s to s minus 2. Whereas this one, you have to take the Laplace transform of e to the 2t, take the derivative of it, and then take another, and derivatives are harder than just replacing by s minus 2. This one, however, has both t and e of t be multiplied to the function sine of t. So you're going to have to do both. I have both here. You're going to have to do both. It's up to you which one. So, I mean, in the end, you're going to have to kind of do both. I'll probably just say this is like my f of t function. I'm going to say all of this. E of t times sine of t, all of that is my f of t function. That's getting multiplied by t. So I'm going to look at the case where n is equal to 1, which is already written here. So if I'm labeling this thing as my f of t, then I'm going to have to take the Laplace transform of that, which is like Laplace transform e of t sine of t. This itself requires the shifting theorem, with c is equal to 1. So you have the Laplace transform of sine. I'm going to write that up here. Laplace transform is sine of b of t. From the table is actually bs squared plus b squared. So we can go immediately, right? What would be the Laplace transform of e to the t sine of t? Given that this on our this Laplace transform that we saw before, the shift is just by 1, so it's going to be equal to this f minus c, is s minus c, but c is 1, so it's be s minus 1 squared plus, and I'll just make the b equal to 1, right? Because the b is equal to 1, right? This b here. And then 1 squared is just 1. So that's using the shifting theorem. And you could multiply this out and just say this could be s squared minus 2s, and then there's going to be plus 2. Plus 2 because there's a plus 1 here, and then we FOIL this, the last term will be plus 1. So that's that one. Now I have to take the Laplace transform, so t times all of this. So the derivative theorem says that, okay, we just decided that this whole thing is my f of t, right? And we just computed the Laplace transform of that right now. So we've done that part. The Laplace transform of t times that is going to be the negative of the derivative of this thing that we just computed. So we'll have to compute the derivative of this, which is like, imagine this is all raised to -1. So you'll have negative, take the derivative inside, which is 2s plus 2. Divided by, this would have been raised to -1, so I'm going to just subtract by 2, and I'm going to put it in the bottom. That's the derivative. So then we just say, it's just, therefore, the Laplace transform of t, e to the t, sine of t, is equal to the negative of this. Which I'm just going to flip this and just say it's going to be 2. No, it's going to be 2s minus 2 over s squared minus 2s plus 2 squared. So you had to do both on this one because it was b multiplied by e of t and t. So that's that one. Let's confirm some of these Laplace transforms. This one requires using the derivative theorem because they're both being multiplied by t. So what I do with this, just there's only derivative theorem. So what we're going to do is we're going to compute the Laplace transform of this, right? This is like our f of t. Can't, so this is like whatever. The sine of t is the f of t. So we're just going to say Laplace transform of sine of b of t. Well, we know that's b over s squared plus b squared. That's from the table. And then let's compute the inverse, the derivative of this. The derivative of this will be just, imagine this is, okay, maybe I'll write it. Imagine this is the same as b times s squared plus b squared raised to -1, which means that my f prime is going to equal negative b. And then you'll have to take the derivative of the inside. So it's going to be times 2s. And then it's going to be raised to -2. So it's going to be s squared plus b squared all squared. So I guess it's the same as -2 bs over s squared plus b squared squared. And then the derivative theorem just says, I just have to take the negative of it. So that means that Laplace transform of t sine of bt is equal to the negative of this, which is just, I'll write it out. Say this is this negative of f prime of s. It's going to be 2bs over s squared plus b squared squared. I'm just confirming, this is just asking you to confirm these things. Okay, so let's do this one's very quick as well. The function we want is cosine of b of t. So the Laplace transform of cosine of bt is it's very similar to the sine. It's just s on the top instead. This will be s squared plus b squared. And then you can take the derivative. This one you have to do the quotient rule because the derivative is with respect to s. here, the top was b, so it wasn't a variable s. This one has s on both. So you have to do the quotient rule. So you're going to do low d high, which is the derivative of s is just 1, minus high d low, which is 2s, over low low. And this top is just going to be b squared, but then there's going to be 2 of these s squared that's being subtracted, so it's just going to be this. And therefore, your Laplace transform of t cosine of bt is just the negative of this, which I'm just going to flip this, so it's just be s squared minus b squared over s squared plus b squared squared, which confirms this one. So I just wanted to confirm these two, because we're going to end up using them potentially later on. So that's it with Laplace transforms. But we got to learn how to go backwards. So it's not that bad to go backwards. Going backwards is like, so let's say you have the Laplace transform of f of t is equal to this capital F of s. How do you invert this? So can you tell me what was the f of t that would have given me that Laplace transform? So this is the schematic here, is like saying, let's say you have f of t. And if you took the Laplace transform of f of t, you'll get capital F of s. This is like taking the Laplace transform. Now, if somebody gave you this, can you go back and tell me what would have given me that? That's called the inverse Laplace transform. Okay, so we're going to try to do that. So now let's say I want you to compute the inverse Laplace transform of s over s squared plus 9. I'm giving you this table, but you're going backwards on this table instead. So we're used to going from like the left to the right, but you got to go from right to left. Which entry on here looks to be the one that you might want to use? T1, T4. T4 because there's a S up here, whereas this one has a B. So you got to go use this one. And this is not much of a stretch, but looking at this table, what do you think the inverse Laplace transform is? Yes. You got it, yeah. Because B must have been 3 to get the 9. It could be -3. It could be -3. So you could also say cosine of -3t, because of course -3 squared would have been also 9. But what do we know about cosine functions? They're even. So this is the same as this. Cosine of -3t is the same as cosine of 3t. So they're the same. So that's fine. That's your inverse Laplace transform. So if let's say I give you the Laplace transform f of s is equal to this, tell me the f of t that would have given me this if you took the Laplace. So let's invert this. Let's invert this Laplace transform. It turns out that you could invert them term by term. So you could say, I want to compute the inverse Laplace transform of 1 over s cubed plus 4 over s squared plus 3. You are allowed to take the inverse Laplace transform of the first thing. And then you could also add it with the inverse Laplace transform of the second one. So this is like the same idea as we had with Laplace transforms, is that the Laplace transform of two things added together, or the addition of the two Laplace transforms. That's just because of linearity, like we went over and talked about that, right? Linearity of integrals. So where is it? It's like a long time ago here. So I said the Laplace transforms are two things added together. You can even pull the constants out, and you can just compute the sum of the Laplace transform. The sum is the sum of the Laplace transforms. That's because the Laplace transforms, they're integrals. It's this improper integral. And so the integral of two things added together are just the addition of those two integrals, and you can pull constants out of integrals. So it's just following from this property of integrals that Laplace transforms can be broken up that way. Turns out the inverse Laplace transform, you could do the same thing. The inverse Laplace transform also has an integral definition, but it's a complex integral. And you may learn that if you took like complex analysis or complex variables, but it's too much for our class. So we're going to only restrict ourselves in order to compute the inverse Laplace transform. We're just going to use the table and go backwards. You can formally compute it using some complex integral, but we won't do that. But this idea that you can break up the inverse Laplace transform of a sum into the sum of the inverse Laplace transforms comes from it's not a hard thing to check. So we know we all accepted this, right? We said that if you had the Laplace transform of two functions, so I'll just say like f of t, and then plus c2 g of t, that you could break up into two. You could say c1 Laplace transform of f of t. And you could say plus the c2 Laplace transform of g of t. But what if I wanted to compute the inverse Laplace transform of both sides? Well, if I took the inverse Laplace transform of this left-hand side, it's like just applying an inverse Laplace transform on this. That's going to cancel with the Laplace transform. So it's going to be c1 f of t plus c2 g of t. And then let me just move over because this is too. And then I'm just going to take the inverse Laplace transform of this side. It's just going to copy this, which is probably not going to fit in this tiny. I'll just do this. I'll just say this is like, that's right. So all I did was I took from here to here. What is it going on? All I did was from here to here, I just took the inverse Laplace transform of both sides. If you took the inverse Laplace transform of this right here, it's like saying inverse Laplace of this, those cancel, and you're just left with this after you take the inverse Laplace transform of both sides. This side, I just copied it completely. This thing is the same as this, the whole thing, but with the inverse Laplace transform written in front of it. And then you just can see that this right here is this. And this right here is this. There's one thing you have to note here is that the inverse Laplace transform of g of s, because g of s, I'll just say, what is g of s? G of s is the Laplace transform of g of t. And f of s is the Laplace transform of f of t. So it'll be inverse Laplace transform of f of t, which is just f of t. Inverse Laplace transform of Laplace transform of g of t is just g of t. And so this is the proof. Okay, so linearity of inverse Laplace transform just follows from linearity of Laplace transforms. Knowing that Laplace transforms satisfy this linearity property is enough for you to, show that using this, that the inverse Laplace transform must also satisfy that same linearity. So we can break up this function into two if you want to compute the inverse Laplace transform. So what's the inverse Laplace transform 1 over s cubed? You're going to probably look at which entry on this table to go backwards. We're looking at this one. I'm going to probably look at one of these. Just trying to compute. It's not this one probably, or nor is it these ones. The only one that's going to ever have a hope of having an s cubed is the last one, right? But in particular, what is the n? Yeah, n is 2. So when n is 2, we would get, it would be 2 factorial, which is just 2, over s cubed. But the one we want is 1 over s cubed. So what we're going to do is we're going to compensate for that. So I'll just make a note here and say, okay, we all agree that this 1 over s cubed can be rewritten as 1 over 2 times the 2 over s cubed. There's a reason why I'm writing it this way. But we know that this is definitely true, right? Because if you had a half times 2s cubed, you would get 1 over s cubed. I'm just writing it this way And there's going to be a nice reason for writing it this way. Plus, I'm going to do the inverse Laplace transform of this right here is 4s squared plus 3. Which entry do you think we would use for that one? It'll have to be the third one because there's no s up here. It's just a 4 right here. So that's a constant. And in particular, you'd have to use this third one with b equal to what? Yes.
It was like s squared at the top.
S squared at the top is going to probably be like, you'll have to use one of, well, there's other versions. We can't do an s squared on the top because on our table, we only have s right here. But this one's 4 on the top, and then s squared plus 3 on the bottom. What must b have been? This is harder. You might think it's, square root of 3 because the bottom is 3 here, and you just know that has to be b squared has to equal 3. Some people might also think that it's 4 because the top is 4, but you have to actually use the square root of 3. I mean, you could do plus or minus square root of 3, but we'll just keep it positive. If you did minus square root of 3, you could still make it work as well. The reason why we have to choose the square root of 3 is because this s squared plus 3 on the bottom, that one we have to make sure we have. The top could be, you can compensate for the top by multiplying by something, but you can't fix this bottom part. So what I mean here is if I took b is equal to square root of 3, then that means it's going to be square root of 3 over s squared plus 3, which is going to look almost like this, but it has a square root of 3 here. So I'm going to write that here. But we can always compensate for this by multiplying by. I want it to be 4 up here. Well, I'll make it 4, and I'll divide by 3, right? You could always do this. This right here is the same as 4 over s squared plus 3. You all agree that that's the same, right? Because you're just multiplying by 4, and then the square root of 3 cancels. So I've not changed anything. I've just rewritten what's inside these inverse Laplace transforms with some multiplicative factor times the piece that we actually know the inverse Laplace transform of. And because due to linearity, which is down here, it's saying that anytime you have C1 f of s, C2 capital G of s, you could split this into 2 separate inverse Laplace transforms. And not only that, you could pull the C1s out. And these are like our C1s. So we could pull these out. So we'll have half times the inverse Laplace transform of 2 over s cubed plus 4 over square root of 3 times the inverse Laplace transform of square root of 3 over s cubed plus 3. But we went through all this trouble to already know what's the inverse Laplace transform to 2s cubed. We looked at this table with n is equal to 2, so that's t squared, plus 4 over the square root of 3 times, what's the inverse Laplace transform of square root of 3? S cubed plus 3. It's this entry on the table. So you're going backwards, so it's like what? Yeah, sine root 3t. So that's the inverse Laplace transform of that one. Okay, so yeah, so the goal now is to do a few more Laplace transforms, and then we're going to have to use the Laplace transforms to finally solve a differential equation. Yes.
Will Laplace transform be on Tuesday?
No, the Laplace transform will be on the final. So yeah. And I was thinking about it this morning. It's going to be kind of intense or probably impossible for me to do the extra inverse Laplace transforms and apply it to solving differential equations in just one class period. So I was thinking maybe what I'll do is, I know people may need to leave, on Monday after 15 minutes because they have a class after, but I think this room is still open. There's no class that comes in until like 2 o'clock. So I'll just like continue until I can comfortably finish like covering how to use Laplace transforms to solve differential equations, but you're not obligated to stay. Everything will be recorded. So if you have to leave, the recording will be available. So So that's but you can stay if you want to see that material live, and then we'll have our test on Tuesday, and then, yeah, that's probably what I'll have to do. Otherwise, the alternative is that I'll just have my 15-minute class on Monday, and then I'll separately record a video of myself talking about how to apply it to solve differential equations, and then you'll just have to watch that video separately. But I think it just makes sense that I do that just standing here and staying longer. And for those of you who could stay and would like to see me live, you could just stay and then you can watch it. But if you can't stay, that whole recording will be available. That's probably the best way. If I can manage to finish it, it'll just be like how I just have to finish it. And I don't think it'll take longer than 30 more minutes extra past the thing, but however long it takes. If I can manage to finish it in 15 minutes, then that's great. But I'm thinking I might have to go a little over, just a little bit. Yeah. Have a good weekend. I do have office hours now, so if you want to stay.